We're now going to apply our criteria for aromaticity to heterocycles. And what heterocycles are, so the hetero term just means different, so that means we have a cyclic compound with atoms other than just carbon and hydrogen. So those atoms, typically nitrogen, oxygen, and sulfur. In this case, we have a 6-membered ring with nitrogen. This particular ring is pyridine. But we're going to go through this in the same way that we would any other example. Now, recognize that the nitrogen, we have 3 bonds shown, the double bond and the single bond. But that nitrogen does also have a lone pair on it. So let's go through and apply our criteria. It's certainly cyclic. Is it completely conjugated? Let's put a p orbital everywhere we have a double bond. Every atom has a p orbital, so it is completely conjugated. Next, is it planar? Well, we have a completely conjugated ring. There's 6 atoms in the ring, so that will be planar. Finally, our pi electron count. Let's count our pi electrons. We have 2 in this double bond, 2 in this double bond, 2 in this double bond. We don't count the nitrogen lone pair for anything here because the pi electrons for that nitrogen are already taken up with the pi bond. So this can't also contribute. So you can't kind of double dip on that atom. Since it's already accounted for here, we don't need to worry about the lone pair. We have 6 pi electrons. 4n plus 2 equals 6. N equals 1. That rule's also met. So pyridine meets all the criteria for aromaticity. I want to take this opportunity to look just a little more closely at the orbitals around the nitrogen and its hybridization. So when we have pyridine, I'll draw it on its side here. If you determine the number of groups around that nitrogen, we have the single bond as a group, the double bond is a group, the lone pair is a group. 3 groups, the hybridization of that nitrogen is sp2. So when something is sp2 hybridized, you should immediately know the 4 orbitals that are involved on that atom. We have 3 sp2 orbitals, and we have a p orbital. So one common question that might be asked here is, in what type of orbital does a lone pair reside? Well, let's draw this out one more time. Okay, and on that nitrogen, remember that the pi bond uses the p orbitals. So here's a p orbital on the nitrogen, a p orbital on the carbon. That's going to overlap on the top and the bottom to form the pi bond. So that takes care of the p. But we still have the 3 sp2 orbitals. So what are those used for? Well, one of the sp2 orbitals is used to make the sigma bond with the neighboring carbon. Another one is used to make the sigma bond with the other carbon. And then the third sp2 orbital that's where the lone pair is going to reside. So that takes care of our 3 sp2 orbitals. So then, to reiterate what I said above, that lone pair, it resides in an sp2 orbital, so it does not contribute to the pi electron count. In order to contribute to the pi electron count, it would have to be in a p orbital involved in the aromatic ring. Here is another heterocycle. This one is a 5-membered ring with a nitrogen. This one is known as Pyrrole. Okay, in terms of the criteria, it's cyclic. Is it completely conjugated? Well, let's take our picture and we'll put a p orbital everywhere we have a double bond. But finally, the nitrogen, remember that it has a lone pair. And if that lone pair resides in a p orbital, it will be completely conjugated. So let's put it in and see what happens. So we'll say it is completely conjugated. If the lone pair is in a p. Basically, if putting it in a p orbital makes it aromatic, then it is. If putting it in the p orbital makes it anti-aromatic, then it won't be, and it will just be non-aromatic. So the next thing, is it planar? Yes, assuming that lone pair is in the p orbital. Finally, Huckel's rule, 4n plus 2. What does that equal? 2 from this, 2 from this pi bond, and 2 from the lone pair. 6. N equals 1, so that's met. So all the criteria here is met for this compound to be aromatic. So this one is different than pyridine in that the lone pair resides in a p orbital. So if we draw out a p orbital picture for Pyrrole, so the nitrogen is sp2 hybridized. We use sp2 orbitals to form these 3 sigma bonds. And then we have a p orbital on the nitrogen. That's where we'll put the lone pair. And then all of our other carbons that are part of the double bonds, those have p orbitals. Just to give you a couple of similar heterocycles that you should know. A similar one where we have oxygen instead of nitrogen. This is called Furan. Again, the oxygen has lone pairs. And then the sulfur counterpart, this is called thiophene.